Good evening and welcome to the St. Louis Zoo. My name is Jim Jordan, Curator of Education, and it's good to see another big turnout for our second in the Science Seminar Series. We've been co-sponsoring the series now for well over 12 years with the Academy of Science, and I'll be introducing in a minute a representative from the Academy who'll tell you of some of the other opportunities that they have and introduce our speaker. This year, we're partnering with the Academy of Science to bring a new speaker here at the zoo that has a strong zoo and conservation theme. And I just want to mention the next one coming up, since it's on November 17th on Tuesday, and it's called Return of the Peregrine Falcon. Jackie Fallon is the Midwest, well, actually for a couple states in the northern Midwest, the recovery plan coordinator, and she's also connected with the Midwest Peregrine Society. So she's been involved in a number of years looking at the recovery plan. She also has her own peregrine that she'll be bringing in if you want to meet one of the coolest bird of prey up close. So that's 7:30 here on November 17th. We invite you back, and people have been picking up the science seminar flyers, so there's lots of great programs coming up this fall and into next winter. With that, I'd like to introduce Peggy from the Academy of Science. She'll tell you of some other things and also introduce our speaker.
Welcome. We are very pleased to be partners with the St. Louis Zoo on this long-running and popular science seminar series covering current and timely topics in science. Many of you are Academy members and friends. For those of you who are not familiar with the Academy, I'd like to take just a few moments to tell you a bit about who we are and mention a couple additional upcoming science seminars. The Academy is a local nonprofit that has been serving the St. Louis community and surrounding counties since 1856, with a long-standing mission to advance the public understanding of science and inspire the next generation of scientists. We continue to celebrate more than 150 years of community service by offering a broad range of free and low-cost public science programming, collaborative science seminar series, trips and tours highlighting science at venues throughout the region. You can find more information on the Academy and our community-wide events and programs by visiting our website. You may also visit us on Facebook or Twitter, or pick up some of our literature just outside the auditorium on your way out. If you'd like to receive e-notifications of upcoming Academy and St. Louis Zoo public lectures and events, there are sign-up sheets and clipboards that I'll be passing around. Tonight, I would like to welcome our students. Meet me in the lobby afterwards, and I have little stickers for you students that may need to verify your attendance with your teachers. We're very happy that you're with us tonight. Tomorrow morning at 10:30 in the morning, if you're available, University of Missouri, St. Louis Public Policy Fellow and political scientist, Dr. Dave Robertson, talks about climate change and public policy at the Kirkwood Community Center, and this is open to all. It's at 10:30 tomorrow morning. I also want to point out on Thursday evening, November 19th, is a brand new series at Kirkwood High School. We will be welcoming Washington University biomedical engineer Dan Moran, who talks about computer-brain interface. For those of you who are students and parents, the doors open at 6 that night with a number of local organizations on hand to talk about summer and other science opportunities. That is a kickoff event for Kirkwood, and students attending 3 to 5 of the Kirkwood Seminar Series and if they write about their experience, are eligible for one of two $250 college scholarships that will be awarded in May. And I'd like to add a little bit about that seminar on the 19th. Dan Moran has been working in the biomedical field for many years, and he has reached a point where a student or a patient can move a video game by thinking without their hands. This is just groundbreaking science. You'll see the research that led up to that, and they're really hoping that this is going to help the paraplegics in the future. And that is at Kirkwood, and it's open to all. With that said, I'd like to introduce tonight's speaker, Dr. James Buckley. Okay, wait a minute. But let me tell you about him. Dr. Buckley earned his doctorate in physics from the University of Chicago and completed his postdoc work at Harvard-Smithsonian Center for Astrophysics, studying with Trevor Weeks, head of the Whipple scientists. In 2004, he received the Academy's Outstanding St. Louis Scientist Innovation Award. He is currently Professor of Physics and Fellow in Arts and Science with the McDonnell Center for the Space Sciences at Washington University of St. Louis. Dr. Buckley is here with us tonight to present highlights from high-energy astrophysics, a field of astronomy that studies some of the most energetic processes in the universe and seeks to uncover some of the fundamental questions about the formation of galaxies and the makeup of our universe. He'll share how his field of gamma-ray astronomy probes these violent processes and may provide a means of detecting the universe's dark components, from black holes to the dark matter. Won't you please now join me in welcoming Dr. James Buckley.
Okay, it's working, I think. Okay, I'm going to talk about what I consider to be some of the most violent places in the universe. Although being at the zoo, maybe the Big Cat Canyon or something like that is more violent. Thinking about maybe getting permission to use some lions or tigers in this, but I thought that might be a little bit dangerous. But anyways, also I will avoid making jokes about like the south side of Chicago where I went to graduate school and so on. I did that once and it didn't go over very well. So anyways, but really what I'm going to be talking about is a lot of the science that relates to my primary research, which is in gamma-ray astronomy. And this is a picture of the experiment, the Veritas experiment in southern Arizona, about 30 miles south of Tucson. Which we've just completed a few years ago, completed construction of this. And after just a few years of data taking, we have quite a few discoveries of some pretty amazing things going on, like trillion electron volt gamma rays from exploding stars and supermassive black holes and search for dark matter and so on. So I'm going to try to give you some background that ties into this experiment a bit. Let's see. Okay, so I'll start with just my own kind of personal perspective. So I got interested in astronomy in high school, and I think largely because of Carl Sagan and this wonderful Cosmos series that I think a lot of you that would come out tonight of your own free will must know about. It was just a marvelous series. He was a marvelous person. And about that time, my family would vacation in northern Michigan. And what I would typically do is around August, when we went on vacation, I would go out at night on a long dock and lay on my back and watch the stars. And this was great because I was away from city lights, and you could see the Milky Way, you could see the Perseids meteor shower, and it was just a fantastic thing to do. And so that was kind of where I guess I got my love for astronomy. And I have to say that the experience of laying on a dock in the middle of Long Lake in northern Michigan watching the meteor shower is not exactly a violent experience. It's a rather tranquil, peaceful experience. Looking up at the stars, you don't see much action. I mean, it's a relatively, kind of a peaceful experience. But what I'm going to do is try to show you, starting with those kind of observations, show you some points in the sky, which you've probably looked at many times, that have some very strange things going on. So I'll start, I hope you can see this okay, with a little movie of what the night sky might look like, looking roughly north. So here's Polaris in St. Louis at this time, on this night, using this Starry Night software. Which is kind of, there are a lot of these ephemeris programs, some free, some to buy, they're really fun to play with. And you can see the stars rising and setting, and you can count the number of stars. It isn't that many due to the night sky brightness here. Here's the moon coming up, and the moon and the sun. Okay. Now, you can identify a lot of these things, and we want to remember some of these names. So one thing you might see tonight is Cepheus. Turns out there's a very interesting variable star in Cepheus I'm going to tell you about. There's Andromeda coming up here. Looks like kind of a bent A. That's a very interesting region of the sky. Cassiopeia, I'm also going to talk about something in Cassiopeia, a supernova remnant. It kind of looks like a W. And later in the night, you'll see the Big Dipper, Ursa Major, coming up, which everyone recognizes. Now, of course, these drawings are just, they're just aids or something to identifying points in the sky. They have no real meaning. These stars are not necessarily even close to each other. They're just kind of accidental collections that people identified and gave names to. So now, if we weren't in St. Louis, and I don't know if it's dark enough in this room to see this, the night sky might look like this. So I've turned off the city light, and you can start to see a faint milky band over here, which is the galactic anti-center region. So it's part of the galactic plane, but the galactic plane in the opposite direction of the center of the galaxy. And you can just see a lot more stars. So this might be what it looked like. And of course, I've sped up time, so we're watching the whole night. We're watching the stars rise and set. They rise and set just pretty much like the sun, although this day of stars rising and setting, a sidereal day, differs from a solar day by 1 day every year. If you think about it a little bit, you can convince yourself that that makes sense. All right. Now, whoops, did I go backwards here? I think I did. Okay. Now, if we zoom in this region near Andromeda, we see the most distant object that you can still see with your naked eye at a dark site. So if you go to northern Michigan, you go to Kansas somewhere, this is the Andromeda galaxy. You might be able to see it if you went a little bit out of town this time of year, got some binoculars, you look for a little fuzzy patch near Andromeda and kind of zoom in on it. Maybe I'll go back and do that one more time. Whoops, sorry. So. Now, the Andromeda galaxy, being the most distant object that you can see with the naked eye, is a good point to start talking about kind of scale of the universe and distances. How do we figure out the distance to the Andromeda galaxy? Well, if you had a 100-watt light bulb and you measured its brightness at one distance and you measured its brightness at another distance, you would find out that the brightness fell off like 1 over the distance squared. There's a 1 over r squared law there. So if you knew how bright the light bulb was, say 100 watts, you would know how far away it was by measuring its brightness, right? So you could calculate that distance d. Well, I'll talk about this in a little bit more detail later, but you can see these individual stars that you can resolve in the Andromeda galaxy, and you know about how bright they are in our galaxy. So say you can measure the distance to those stars in our galaxy and how bright they are at a certain distance. Then if you measure how bright they are in Andromeda, you can calculate the distance from this 1 over distance squared law. And what you find out is that that means that the Andromeda galaxy is a distance of about 2.5 million light years from us. That's the distance light would travel in 2.5 million years. That also means the light we're seeing from Andromeda was emitted 2.5 million years ago. And it's as simple as that. There's very little, I mean, it's a very simple calculation. You can do it with just a little bit of algebra, not much of a way out of this. So we know that the light's been coming to us from this galaxy for at least 2.5 million years. So we know right now a number of things. We've seen one of the nearby galaxies. It took a while for people to really convince themselves that these things that they originally referred to as nebulae, that some of these things were actually little island universes made of 10 billion stars. That took a little bit, and I'll tell you a little bit more about how we know that. But once you demonstrate that, and once you measure the brightness of some stars, especially if you can find some stars that you really know a lot about, called standard candles, kind of like your 100-watt light bulbs, then you're led to the conclusion that this thing is 2.5 million light years away, and the universe is at least 2.5 million light years old. And as you go, 2.5 million years old. And as you go further and further out, you eventually see things that are a billion light years away, and you know the universe is at least a billion years old. And I think this is a neat and very simple and inescapable fact that you can learn without too much sophisticated math or anything like that. Now, that Milky Way, if you take a time exposure with the camera, and these are a couple of images I found on the internet, is really an impressive thing. So this is our own galaxy. We are like living inside of kind of a pancake of stars, and when we look out, since we're inside of the plane of the galaxy, we see this narrow band on the sky. This band is formed of tens of billions of stars. That's about how many stars there are in our galaxy. The center of the Milky Way, which actually might be kind of here, it's in kind of a dark region that's obscured by dust. The center of our Milky Way is about 24,000 light years away. And I just want to use this as a starting point to ask, well, how do we really know so much about these little points of light? How do we know they're stars? How do we know what they're made of? How do we know how far away they are? How do we know all this stuff? So I want to talk about some of that today. The first big clue comes from spectroscopy. So if you break up the starlight with something like a prism or a diffraction grating into its constituent colors, you see the colors of the rainbow. But you can also see, and these are spectra of, you can consider each of these bands to be a star of a certain class. So each of these are different measurements made for different stars, and the stars are named O stars to M stars. So these are different classes of stars. And what we see is, for each of these stars, we see this broad spectral distribution, but we also see these dark lines, these narrow dark lines. And these turn out to be features that come from absorption of light, the black body radiation, the kind of light that you get when you heat something up. Everything that's hot glows, and it glows with a color that depends on its temperature. That light gets absorbed by the atoms in the stellar atmosphere, and so when the light has a wavelength and a corresponding frequency that such that the energy of those photons correspond to the difference in the energy level of in the atom, you can get absorption. So if you think of your chemistry classes, that's where this comes from. So we can identify different patterns of emission or absorption lines. We can use these kind of like fingerprints of different chemical elements, and we can tell how much of what the stars are made of, even though they're just little points of light that we can't even resolve with the best telescopes. We can still figure out something about what they're made of. We can also study these patterns and tell something about the temperature of the stars. Remember I said, you've heard of a red hot poker or a white hot poker or something. The color that something glows tells you about its temperature. Similarly, the intensity of these lines tells you something about the temperature. And this, by the way, this organization of stars by their spectral classification, this was largely done by people like Annie Cannon at Harvard University and around a little bit after the turn of the century. So this was a very important first step. Before people even really had a full-blown quantum theory to explain it, this was the first step to understand these stars. Now, there's another important clue out there to learn a heck of a lot about what we're observing. And that clue comes from the Doppler shifts in those spectral features. So we see a pattern, a fingerprint of, for example, hydrogen or helium or something in these stars. But sometimes that pattern is shifted a little bit to shorter wavelengths, to the blue, and sometimes a little bit to longer wavelengths, to the red. And there's a very simple explanation for this, which I was showing in this little animation here, that if a source is emitting light and moving, in this case moving to the right, the waves will be kind of bunched up in the direction of motion and kind of spread out away from the direction of motion. So if you're an observer over here, you're going to, and the source of this light, say a star, is moving towards you, you'll see a shorter wavelength. If it's moving away from you, you'll see a longer wavelength. And the amount of this red shift or blue shift tells you about the ratio of the velocity of that object to the speed of light. So again, just this very simple, miraculous kind of clue that we're provided to figure out an awful lot about what's going on in galaxies and stars and so on. I'll use this as time goes on. Now, another thing you should know is that the visible part of the electromagnetic spectrum is only a tiny part of this spectrum that goes all the way from radio waves to gamma rays, which is what I'm going to be talking about primarily today. And all of these things can be explained by one underlying physical phenomenon, which is oscillating electric and magnetic fields in space. That's what they all are. They're just oscillating fields that oscillate with different frequencies and different wavelengths. So our sun emits most of its power in this wave band, so our eyes adapted to see light in the visible range. If we had a different kind of sun that maybe primarily emitted in the ultraviolet, we might have developed ultraviolet eyes. Now there is also radiation being emitted by our sun at longer wavelengths in the infrared and radio and at shorter wavelengths, but these rays are absorbed by the atmosphere except for a couple very narrow windows. So again, there wouldn't be much purpose in our eyes evolving to see these things if they were absorbed by our atmosphere. So it's kind of, there's kind of an anthropic principle or something for why we tend to be so focused on this one, no pun intended, on this one narrow band of the electromagnetic spectrum. Now, the instruments that measure this radiation, the most familiar type of instruments are telescopes, optical telescopes. And here's the famous Hale 200-inch telescope on Palomar. But there are different types of telescopes, very different types of telescopes, some of which even are based on satellites and so on. But I'm going to talk about two other ground-based telescopes. One is a radio telescope, which is kind of like a big mirror, or sometimes people think of it as an antenna. It really depends on the ratio of the size of the telescope to the wavelength of light. If it's very large compared to the wavelength of light, you can look at this as just kind of a reflector. But you can detect these radio waves very much like you detect visible light. Oops, sorry, I'm still having problems here, clicker problems. Now, Up here, even above this, the end of this spectrum, comes the region where I'm interested, which is the region of TeV gamma ray astronomy. Here, we somehow can detect these very high energy photons with large optical telescopes on the ground. And that takes a little bit of explaining. First, I want to tell you a little bit about why TeV gamma rays are amazing, or why I think I would call them violent kind of photons. Basically, these are photons that have almost a macroscopic amount of energy associated with each little quanta of light. A TeV is also close to an erg, which is a unit of energy some of you may have heard about. So each photon has an erg of energy. And to get a feeling for how high that energy is, to produce TeV gamma rays on the Earth, you would need to use one of the largest machines that mankind has ever produced, like the Large Hadronic Collider. There's a little guy standing here in the middle. This is just the interaction region in the Large Hadronic Collider, and these are these miles of magnets that accelerate the protons to get up to trillion electron volt energies. And to make one of these gamma rays on Earth, you'd have to do something like accelerating an electron or a proton to 1 trillion volts and slamming it into something else, like another particle, a proton, or something like that. So that's what it would take to do this on Earth. But somehow nature is doing this. Somehow there turn out to be almost 100 of these objects in the universe that are producing these extraordinarily high energy photons. Sometimes they're even putting out most of their power in this normally invisible band of electromagnetic radiation. Now, to detect these photons, when the photons have this energy, detecting them is almost like detecting meteors interacting in the Earth's atmosphere. Each photon interacts, forms a bunch of secondary particles, and leaves behind a streak of light, almost like a meteor shower or something. So this is basically how it works. You have a typical source of gamma rays, like say a supermassive black hole spitting out a jet of relativistic particles. I'll talk about in a little bit. This emits a gamma ray. Emit a gamma ray, please. Which hits the atmosphere. It produces an electron and a positron, an electron and its antiparticle, a positron. That's already kind of neat. Each of those guys can go on and bang into a nucleus and emit another electron, and each of those can bang into something and emit another electron. So you get this cascade of particles. Each of these particles can actually be traveling faster than the speed of light in the atmosphere. You can't travel faster than the speed of light in vacuum, but you can travel faster than the speed of light in a medium, because in a medium, due to the index of refraction, the speed of light is reduced a bit. So they emit something called Cherenkov light. This is the kind of blue glow that you see around a reactor from the energetic particles passing through the water. They're again traveling faster than the speed of light in water, which is roughly the speed of light in vacuum divided by 1.4. And actually I can show you a little cartoon of how this electromagnetic shock wave forms, which looks very much like the cartoon for the Doppler shift. So imagine that, remember when we were looking at the Doppler shift, these guys were getting bunched up in the direction of motion. Well, it's easy to see that if the emitting particle, or whatever it is emitting the radiation, is traveling faster than the speed of light, that these wave fronts kind of interfere with each other and form something which is very much like a sonic boom. When a plane goes faster than the speed of sound, it forms a sonic boom, which comes from the same type of interference. Well, this is an electromagnetic shock wave, which is this Cherenkov light, and that's what we detect. So what we end up seeing is we build arrays of telescopes, we track various points in the sky, and what we see are streaks of light, which we image stereoscopically with several telescopes, and they point back to wherever they came from, like a supermassive black hole or a exploding star or something like that. And we can even collect a lot of these events and make images in trillion electron volt gamma rays of those regions of the sky. So that's the basic idea. Okay, now what we've seen so far with Veritas, we've seen about 25 sources, and this is a weird plot. These are called galactic coordinates. This is just a way of plotting everything on the whole sky by kind of taking the sphere around you and unwrapping it and turning it into a football and then putting a point everywhere in the sky where you see something. And we see a lot of different types of objects, but they're all pretty wild things. Of these 25 objects, we see shock waves from exploding stars, supernova remnants. We see binary systems with orbital periods of less than a month of something like either a pulsar or a black hole orbiting around a massive B star. We see emission caused by the intense magnetic fields around compact neutron stars. These are like stars that have the density of a nucleus, the mass of the sun, and a size that would fit within Rhode Island. So these are crazy, crazy objects. And we've recently seen, we see flares that last minutes. So usually you think you have to look a very long time to see any changes in the heavens, right? But we see flares that last for minutes of trillion electron volt gamma rays from jets being emitted by 100 million solar mass black holes. I mean, this is all, this is our bread and butter, kind of work that we do. So of these 25 objects, they're all what I think is fair to call kind of violent processes or extreme processes of nature. And they just turn out to be more ubiquitous than we ever would have thought, say 10 years ago, when we only saw 2 of these things. We saw the Crab Nebula and 1 active galaxy when I started this business. So it's really kind of taken off recently. Okay, now I'll give you a little bit of background information, and to check the time here, which I can never seem to find. So I'm going to start out by telling you a little bit about astronomy, just so you can kind of see where some of these measurements fit in. So I'll start with kind of the life and death of stars. So stars are born in and die, much like human beings, unfortunately. A star like our own sun will live for about 10 billion years. It's already about halfway through its life, so it's a nice kind of adolescent, or maybe it's middle-aged like I am, I'm not sure. But stars are born in the collapse of dense clouds. For example, everybody knows the constellation Orion. If you look in Orion, there's a nebula that you can see with binoculars or a small telescope known as the Orion Nebula. And this is a stellar birthplace. This is an area with very dense clouds that are forming stars. Eventually what happens is these things, they collapse under their own weight. They become denser and denser, hotter and hotter. And eventually the rate of collisions of the protons or the hydrogen nuclei in these things becomes so high, and they're hitting each other with so much energy that they can actually fuse and ignite nuclear fusion, and then the star begins to shine, as, for example, these young stars in the Seven Sisters, or Subaru galaxy as it's called, in Japan. And I think this is supposed to be the symbol on my Subaru Legacy, but somehow I can never quite figure out how it matches up. But anyway, so these are some young stars. Now, these stars derive their energy by having protons bang into other protons, or hydrogen nuclei, form deuterons, which is a proton and a neutron. These guys get together, a deuteron gets together with another hydrogen nucleus and forms an isotope of helium. These 2 isotopes get together and they form a normal helium nucleus, 2 protons, 2 neutrons, and a couple of little catalyst guys fly off. They just kind of went along for the ride. And what happens in this process, whoops, oh yeah, sorry, I'm a little trouble seeing this, that this process manages to take almost a full percent of the E equals mc squared rest energy of those protons, 0.7% of that energy, and turn it into radiation. So it's actually pretty efficient. It's 0.7%. There are more efficient processes than this in the universe, though. It turns out that, if you have a very, like a black hole or a very dense star, when material falls into that gravitational potential well, you can actually extract up to 30% of the rest energy through this accretion process. But this is still a pretty efficient process. But eventually, you burn up all of this fuel, and that's a bad thing, because this fuel was also, and this source of energy was heating up the gas, creating pressure, which was holding off gravitational collapse. So when you burn up the hydrogen, leaving behind helium, the star starts to collapse again. And the helium gets compressed until it ignites nuclear fusion. Now that takes a little bit higher temperature, because the helium nucleus have a higher charge and they have more of a Coulomb repulsion, so you have to hit them together a little harder for them to kind of stick and fuse. Well, then the helium forms heavier elements like carbon and oxygen, and those fuse, eventually form up to iron, and then you have nowhere to go, because iron has is kind of the most stable nucleus per neutron or proton. It's at a minimum in the energy, and there's nowhere else to go. So eventually, depending on the mass of the star, you'll burn things to carbon or oxygen and then stop, or you'll burn things to the point that you produce iron and then you'll stop. And then what happens is there's really nothing in the form of fusion or something to create more energy to hold off collapse. And what comes next gets kind of weird and kind of interesting. So let's first look at a star like our own sun, mass of our sun. What's going to happen is when it gets to carbon, for its mass, that's where things are going to end. Okay? So it won't be massive enough to compress that carbon to the point where it burns to iron. So you're going to be left with this carbon nuclei, and some electrons. And the thing is going to compress and collapse further and further and further until eventually we're trying to pack the electrons so tightly into this core of this star that there's a strange quantum mechanical principle that kicks in called the Pauli exclusion principle. This is the same thing, if you remember, from chemistry. I'm hoping that a lot of the students out there have seen a little bit of this in chemistry. When you consider filling the orbitals of an atom, you can only put 2 electrons in each orbital, then you go to the next higher energy orbital and so on. That's because of the Pauli exclusion principle. It's the same principle. You can only pack the electrons in so tight, and then you can't do it anymore. So that forms a new type of pressure, which for some reason has the name degeneracy pressure. It has nothing to do with like degenerate people or anything like that. I don't know where that term comes from. And that degeneracy pressure will keep the thing from collapsing further. And so for our own sun is going to end up as a white-hot ember of very dense carbon supported by electron Pauli exclusion degeneracy pressure. And since dense carbon is what makes up diamonds, I think you could call this thing, you know, in the words of Pink Floyd or something, a crazy diamond that's left over, that starts out white hot and then slowly radiates, cools, and fades away. That's the way our sun will die. Kind of sad, but you know, nothing is forever. So the problem, though, with some other stars is that if you have an even larger mass, that electron degeneracy pressure is not enough. And sometimes you'll have a white dwarf in a binary system. Like fully half of stars out there are in binary systems. We're just pretty lucky that we're not on a planet around a binary star, because we never would have had a stable enough climate to evolve life. So many little miracles like that about our own planet that make it a kind of a rare place to live. Actually, I recommend a book called Rare Earth, which is just a great introduction to astronomy, really, from the perspective of evolution of life on this planet. But a lot of stars are in binary systems, and sometimes those white dwarfs start getting mass accreting onto them from another star, and eventually get so much mass that the degeneracy pressure can't even hold off gravitational collapse. And what happens is that they're pressed together so hard that the electrons and protons recombine into neutrons. And the whole thing collapses into something called a neutron star, where now neutron degeneracy pressure holds off further collapse. But sometimes even that isn't enough. So here I have a little cartoon of an exploding star, a supernova. This is something that happens on the way to forming this neutron star. So what happens is that as you spend all of your nuclear fuel in a star more massive than our sun, like at least maybe say 10 or 20 solar masses, you get this kind of free fall of the outer layers of the material that collapse in, and eventually at the core you could form a neutron star or something else, like even a black hole. But when that core forms, when the gas falls in, there's some sort of bounce. As the stuff infalls, somehow the material gets stiffer, or it emits a lot of neutrinos or something, and that blows the outer shells of the stars back out, forming a massive shock wave that rams into the interstellar medium. And that shock wave is so powerful that it can actually put a lot of that explosion energy into very energetic particles, like trillion electron volt electrons and protons. And sure enough, sorry, I'm really having problems here. Okay. And sure enough, with Veritas, we actually see the remnants of some of these exploding stars. So here's one supernova remnant, G106 plus 2.7, doesn't really mean much, but we see this extended emission. So we actually see an image in trillion of electron volt gamma rays, and these contours are the radio image of the same supernova remnant. Here's another supernova remnant we discovered with Veritas, which is IC443. Again, the kind of radio contours, and here's the trillion electron volt emission. So we've already seen that these things, as people hypothesize, really are capable of accelerating these particles up to incredibly high energies, and quite possibly explain the origin of cosmic rays, which is kind of an 80-year-old mystery that I think we're making some progress in resolving. Now, another very interesting object we see in our galaxy is one of these binary systems where there's a massive star, so massive that it's blowing off its outer envelopes in the form of a wind onto some sort of compact companion star, which is either one of these crazy neutron stars or maybe even a black hole. And the really cool thing here is, okay, in this case, we don't resolve the size of the source like we did for a supernova remnant, but when we look at these trillion electron volt gamma rays over time, we actually see the source blinking on and off. And I really only have 2 frames here, but I'll just kind of show you 2 frames taken at 2 different orbital periods showing the source turning on and off in trillion electron volt gamma rays. So we see these periodic, this 26-day beacon of TeV gamma rays in our galaxy. This is another thing we've seen with Veritas. And I won't get into too many of the details of that, but this would be an example of emission from something to do with either the shocks formed by these high winds or the intense magnetic fields of this spinning neutron star. Okay, now it gets a little better. So let's talk next about something that happens for the most massive stars when even the neutrons and this neutron degeneracy pressure can't hold off collapse. Now there's nothing left in nature to stop collapse. And that leads to everybody's favorite, black holes. So if you had a neutron star with a mass much more than about 3 times the mass of the sun, there would, as far as we know, there's nothing to stop further collapse. And And as far as we know, this will continue to collapse to a point of almost infinite density. But nature really tries to avoid infinities typically. So why are otherwise responsible scientists led to this conclusion? Well, I'm going to start by telling you how I explained about black holes to my 4-year-old daughter here. So, and then I'll try to get a little bit clearer about this. So basically, the way things went were the following. It was probably a little bit like November or something. We were going out and built a snowman, and by the end of the day, the snowman had unfortunately collapsed. And my daughter asked me, "Well, Dad, why did the snowman collapse?" And I said, "Gravity." Being a smart aleck scientist father. And then I said, and you know, sometimes gravity is so powerful that, believe it or not, there are these objects in the universe where nothing can stop gravity, and things collapse to form these things called black holes. And this is the picture I drew for her about what happens in a black hole. So I drew this snowman falling into a black hole, and I explained some things I'll talk about in a minute. I said, so if this snowman, for example, was falling into a black hole, what would happen is he'd get stretched out really long and thin, and time would move more slowly at his feet than the top of his head, and stars and everything else would get sucked into this hideous vortex of the black hole and so on. And, you know, I think that was, what is the expression now? Too much information, you know, for a 4-year-old. But, you know, so that's kind of my overview. So let's talk about this a little bit more. How am I doing for time? I can't, what time is it now? 8:20. It's 8:20, so we're about 10 minutes from the hour or something like that. Okay. So, well, let me tell you some of the fun things about black holes first, and then I'll tell you how that relates to my research. So here are some fun things about black holes. We can start out without really having to go too far into Einstein's theory of general relativity or anything. We can just look at things from some kind of, you know, more or less just kind of a description of some of the things that happen around black holes. Well, around a black hole, a lot of us have heard that space and time are curved, whatever that means. It is a complicated thing to explain in a lecture of this length, a lecture, you know, of an hour and a half, so I don't think I'm going to try. So space and time are curved, which makes light bend and so on. And we've probably all heard the story that around a black hole we have a star of such high density that light emitted at some distance from the black hole can no longer escape. And that distance where light can no longer escape is called the event horizon. We can do just a little bit of simple math based on a calculation that we might do for the escape velocity of a rocket from the Earth. So to calculate the escape velocity, the velocity that you'd need for a rocket to make it off the Earth, what we would do is equate the kinetic energy of the rocket to the gravitational potential energy. And I apologize if you haven't seen this much physics, but you can just, for some of you, I think this will make it a little bit more concrete. So we can calculate the escape velocity as being the velocity for which the kinetic energy when the rocket takes off from the surface of the Earth is just enough to climb out of the gravitational potential well. And we can solve for that velocity. Well, what Einstein noted, which was very important, is that the inertial mass that shows up in this kinetic energy is exactly the same thing as the gravitational mass. And that's a very deep point. I can't get into it too much, but algebraically we can just cross that out from both sides of the equation. And then just for kicks, for the escape velocity, we can put in the speed of light. And then what we can do is solve for the radius for which the radius and the mass for which the escape velocity would have to be the speed of light or greater. That radius turns out to be 2 times this gravitational constant g times the mass of the object, the star, divided by the speed of light squared. That radius is roughly what we mean by the event horizon. So for an object of mass m, if all that mass is contained within a radius r, such that r equals 2gm over c squared, then we actually have a black hole. We have an object with an event horizon. We have an object for which there's a distance from which light can no longer escape. That's what makes it black, a black hole. Falling into a black hole due to the incredible bending of light and time dilation and so on, we might see something like this. A black region towards the center where no photons can come back towards us, and the rest of the external universe kind of concentrated into a narrow band by the extreme bending of light. Actually, there's a point around a black hole called the ergosphere for a rotating black hole, where space-time is dragged around so fast that you can't even maintain an orbit. That's actually outside of the event horizon. And there's an interesting thing that you can show happens at the ergosphere, which is this is the point at which you can see the back of your own head from the bending of light. So that, I think that would be pretty neat to see the back of my own head. So, okay, so lots of fun stuff with black holes. Now, I want to say just a few things about special relativity, because this is going to help us a little bit with understanding black holes. So this is special relativity on one slide. There's a guy standing here on the Earth with a clock, and a guy on a rocket with a clock. And what I want to show you is that these two clocks appear to move at different rates. So this is this thing people have heard about in the twin paradox, that if two identical twins are born on the Earth, one flies off at a rocket close to the speed of light and comes back, he's aged less than his twin on the Earth. It's actually not a paradox. That's exactly what happens. It's a little tricky to resolve it exactly, but so, you know, this is a crazy thing that really happens. That it happens is something that's part of my everyday work, because when I look at gamma rays interacting in the atmosphere or protons interacting in the atmosphere, I see particles on the ground called muons. Well, these muons have a lifetime that is so short they should never make it to the ground. The only reason they make it to the ground is because of this relativistic time dilation. I want to show you just quickly where this comes from. If I replace that clock, that little stupid alarm clock, with a light clock that works by taking a pulse of light, bouncing it off of a mirror, having it come back to a detector, make a little tick, and then repeating the process. So this clock ticks by bouncing the light back and forth off the mirror. Then I take into account the amazing and crazy fact that the speed of light is a constant in every frame of reference. Totally nuts. The speed of light emitted from an object moving at half the speed of light is still the speed of light. A crazy observation that people have made. Doesn't make any sense. Doesn't fit in with our idea that if you throw a baseball on a train going 20 miles an hour and you throw the ball at 80 miles an hour, you think the ball should be moving at 100 miles an hour. That's the Galilean logic. If you emit a photon from a train going at half the speed of light, at the speed of light, from the standpoint of an outside observer, it'll still move at the speed of light. That forces us to a shocking conclusion, which is that, okay, my light clock, from the standpoint of an observer traveling on the rocket, ticks with a time that's 2 times this length divided by the speed of light. But from the standpoint of a stationary observer, the stationary observer sees the light make kind of an angle, hit the mirror, which is a little bit further along, then come back to the detector, which is a little bit further along. So the stationary observer sees the light take this longer path, but the speed of light is still the same. You just use the Pythagorean theorem here. I promise you it's not too hard. And you end up with the fact that the time that it takes for this clock to tick is now given by a rather different formula. It's this 2L over c divided by this crazy factor, the square root of 1 minus v squared over c squared. This factor is named after Lorentz, who's one of the people who figured out this transformation was necessary. This Lorentz factor is sometimes given the symbol gamma. And what it tells us is that the times measured by the stationary observer traveling with the clock, this is sometimes called the proper time, and the observer that's left behind, that's looking at the moving clock, those times are different by a factor called gamma. And that is an amazing fact that is borne out again and again by particle physics experiments, if not by our common experience. Now, as I approach the hour, time is a good thing to talk about here. So now I want to talk a little bit about space-time diagrams because they're going to help us to understand black holes. And at some point I'm going to wind down and ask you guys for questions. I have probably too much material here, but let's talk a little bit about black holes. And so this is a space-time diagram, and this is a graph where I don't just plot the position of something, I plot the position and the time that it happens. So point on this graph, which has like position along one axis and time along the other axis, is an event. Like an event would be like a flash going off on a camera. A series of events I could graph, and that series of events, oops, I guess I think I have this arrow pointing to the wrong thing, would be a line like this. This would kind of give a space-time trajectory, or what's called the world line of an event. So this could be kind of the path in space and time of a car moving at some velocity. Now, another interesting concept is that of a light cone. A light cone, which I've drawn here, is basically a region of space that contains all of the possible futures for, say, an observer or a person at this point on the space-time diagram. Since this person cannot move faster than the speed of light, he can never access these regions of space outside of the light cone. If he travels as fast as possible, he can only sample the regions of space-time within his cone, which kind of extends out to infinity. So if we watch this observer, if we plot his position at different times, we see that he's moving to the right with time. That's what this plot means. And we can keep redrawing his light cone, which tells you where he could possibly go if he changed his course, because he can't travel faster than the speed of light. You can draw another such observer. That first observer I drew, you might have noticed, was traveling very close to the speed of light. This person was traveling a little slower. And now for my goofy thing. Those light cones always made me think of these crazy Elizabethan collars that you see on dogs to keep them from biting themselves, you know, like when they get, you've seen these things. It's just such a funny sight. And it's kind of a similar concept, too. This poor dog can only kind of see within this cone. So it is kind of this idea of the possible futures of the dog are kind of contained in this Elizabethan collar. And I thought it would be fun to draw the world lines of a cat and a dog wearing Elizabethan collars as the dog chases the cat. So that gets, they catch up with each other and something bad happens probably. So, so this is a useful picture for understanding black holes, and I'll show you why. It's a complicated picture, but it's an important one. So there were some very smart people like Einstein who came up with this field equation that said how the curvature of space-time is related to the energy density of space-time. He wrote this equation, but he didn't really have any solutions for it. So there are other smart people like Carl Schwarzschild that came along and solved this equation for some very simple cases, like a spherically symmetric star or something like that. And they came up with something that related, that told us how to calculate distances on a space-time diagram. Now, the long and short of it is, if I make a space-time diagram of a collapsing star. It kind of looks like this cone, so this would correspond to the radius of the star, which is shrinking down, 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 until it falls within the Schwarzschild radius, which is this event horizon, the point at which light can no longer escape. So this is kind of the space-time diagram of the collapse of a star, and then this tube is kind of the Schwarzschild radius plotted again and again along the time axis, so it just kind of stays there. Now, if we consider one of these cats or dogs with his Elizabethan collar falling into this thing, a curious thing happens when this poor beast crosses the event horizon. All of his possible futures are contained within this light cone. And look at what happens. There's a point at radius equals 0 that is in every possible future of that poor dog or cat that's falling into the black hole. And because of copyright things, I didn't want to show this, but you should all watch the Ren and Stimpy episode called Black Hole, where they're the first dog and cat to fall into a black hole and live. You can find it on the internet. It's a lot of fun. But anyways, so these dogs and cats, every possible future for them has this point of r equals 0. So this is why scientists take this idea of a singularity or a point of infinite density seriously, because the certainty with which all matter will fall into this point at r and 0 is the same as the certainty that your life will progress from the cradle to the grave and not vice versa. It's like the space and time are kind of getting switching roles. So the certainty that your time has an arrow that proceeds into the future becomes the certainty that you will keep falling into this point of infinite density. Kind of scary. Now, one unfortunate thing is that on your way to falling into a black hole, something really bad happens to you before you ever get there. And this has a great name. It's spaghettification. And this spaghettification works like this. The force on the head and the feet of an astronaut falling into a black hole are different slightly. This is like the idea of a tidal force. It's a little bit bigger on the feet than it is on the head. And so there's something kind of tugging this poor guy apart. And he kind of gets stretched out, and maybe something bad happens before he ever crosses the black hole. Well, let's see if something bad really happens. Do a little bit of math. Calculate the difference in the force on the head and the feet. You get a nice little formula. It's kind of interesting. Tidal forces go like 1 over the radius cubed and are directly proportional to the length of the object. So kind of a nice little formula there. And let's just see how bad the tidal forces are when I hit the Schwarzschild radius, the event horizon. What is the tidal force at the Schwarzschild radius? Well, I calculated this, and I came up with a cool little formula I'm very proud of, that the tidal force is something like 1 trillion pounds at the event horizon of a black hole with the mass of the sun for an astronaut that weighs 220 pounds with a height of 6 feet. That's pretty bad. I say that something very bad is going to happen. There's a little snap there. So unfortunately, you would never make it on this journey. Now, we all know you can never call home and tell anyone what happened when you cross the event horizon because no light can escape. But sadly, for a small black hole, you would actually be spaghettified and snapped in half. Now, that's kind of depressing because I would like to think somewhere there's a black hole in the universe where I could cross the event horizon and survive. Well, fortunately, there are. Fortunately, there are black holes with 1 million solar masses. And if this number is 1 million times the sun, then this is 10 to the 6th squared, which is 10 to the 12th. And I only feel 1 pound of tidal forces. So if I can find a supermassive black hole, I at least can experience the infinite. I can't tell anybody about it, but I could survive. And there are such objects, supermassive black holes, and I think this is I'll probably end with this, and I just had too much material. I want to take questions. If people have questions on dark matter, I'll tell you about it. There are such things at the centers of very huge galaxies, giant elliptical galaxies, which are found in galaxy clusters. These things may have 100 times the number of suns as our own galaxy. These crazy things also spit out these jets of material that are traveling so fast that their time dilation factor, that gamma factor I talked about earlier, can be 100. So here are things that are capable of accelerating bulk material to Lorentz factors of 100. That object, M87, is one that we've recently written a paper on, appeared in Science, just I think maybe like this last month. Now we know that there's a monster at the center of these things, because if we look at the Doppler shift so if we take a little slice through the center of one of these galaxies, look at how the spectral lines of stars and gas are Doppler shifted. We see that they're shifted more and more and more, bluer and bluer and bluer, and then quickly switch to redder and redder like this. And what we have is incredibly high orbital velocities around the center of this thing, which by Kepler's law tells us that for this particular object, we must have 100 million suns concentrated within a distance of something less than the distance between us and the nearest star. And there's no way that could be stable. People just pretty much assume it has to end up as a supermassive black hole. And this is a little cartoon that I made with some science artists a number of years back, which kind of shows what's going on. So there's this black hole. We see this material swirling around the black hole. It's falling in, being accreted into this thing, and spitting out these jets of material in which there can be shock waves and other things that accelerate particles and upscatter photons to form gamma rays, for example. And sure enough, we see such a thing from one of the nearest supermassive black holes, M87. This is actually a billion solar mass black hole in one of the nearest of these so-called active galaxies, something like a quasar or something. And here we can see that active galaxy with its jet in the optical, and then using radio arrays we can zoom in to very close to the central object, only something like tens, a resolution element here is something like tens of a Schwarzschild radius. So we're looking very close to the central object. And the amazing thing is, with Veritas, we saw emission from this source. So this is just a little plot on the sky of TeV gamma ray emission. But we also saw variable emission that was correlated. This is an actual movie of the emission from, say, within 100 Schwarzschild radii of the black hole. We saw that this emission was correlated with this emission. And actually that the flares from this object came before the flares that we saw in the radio. So we know that these TeV gamma rays are coming from very close to that central black hole. And I think I had way too much to talk about, so what I'm going to do, I think, is I'm going to stop here, and I had another topic kind of prepared, but maybe if there are some questions on it, I can just take them then, and that was this topic of cosmology and dark matter, but I think this is a good point to stop and just take questions. So. All right? Anybody? Yes, this gentleman here.
Is there a minimum size to a black hole?
There is a minimum size that you could get by forming a black hole by the collapse of a star, and that would be something like a couple solar masses or something. There could be black holes that were formed in the early universe by some process we don't understand. People refer to them as primordial black holes, and they in principle could have any size. As long as the density is high enough, you can see that you can satisfy that condition for the existence of an event horizon. The condition is that you have enough mass inside of a certain radius. But what Stephen Hawking and others discovered is that for smaller and smaller black holes, which have higher and higher curvature, spatial curvature around them, there's a process where in the vacuum, particles and antiparticles are constantly being created and destroyed. It's possible so that the vacuum is constantly seething with creation and destruction. It's possible for one of those two little guys to go into the black hole and the other guy to get out. And this process gives rise to an evaporation, a loss of energy from the black hole called Hawking radiation. So small guys tend to not live so long. And actually, one of the things we've done with gamma ray astronomy is to look for the evaporation of primordial black holes. And actually, if you read The Brief History of Time, it mentions a search by Trevor Weeks, the guy I worked for as a postdoc, that put constraints on the number of primordial black holes there could be in the universe from the non-observation of these gamma ray flashes that you would expect from black hole evaporation. So if you like reading books like The Brief History of Time, you can learn a little more about that. Yes?
13.1 billion light years, the latest gamma ray burst.
Oh, the most distant gamma ray burst that's been observed now? I don't know. You probably know better than me. Is it that far?
Yeah.
Because that's just shy of what we think the age of the universe is, which is about 14 billion years. So, nice. Well, gamma ray bursts are probably, people now think, something like super-duper supernova explosions. They're explosions that maybe are 100 times as energetic as a supernova. And we think that they're the signatures of the birth of a black hole, actually, for really large stars that collapse to a black hole. And there's something different about them from other supernovae. Other supernovae have material thrown out at like thousands of kilometers per second. These things have material thrown out incredibly close to the speed of light. So they have like a relativistic blast wave that they call a relativistic fireball, which gives some unusual signatures. And as you may know, they can outshine briefly, pretty much everything else. The universe are very bright events, and we see them out to the largest distances because they're so bright. So they're telling us about the most distant parts of the universe, the earliest parts of the universe. So they're fascinating things to study. We haven't seen them yet at this energy, but that's one of the things we're looking at. Let's see. I guess this gentleman here in the gray sweater.
In the notes, it said something about the possibility of the dark matter detector.
Okay. I'm going to skip. I mean, boy, did I prepare too much stuff, didn't I? That was really bad. All right, so let me go to dark matter. Boy, so much nice stuff, but let me just go to dark matter. Okay, so it's a long story, but a lot of the universe is made of this dark matter. We know this just by measuring the velocities of stars and galaxies. They're traveling too fast, just given Kepler's laws, for the amount of mass we see in stars and other things. Entire galaxies are held together by in a 10-to-1 ratio by dark matter. We think that the dark matter, well, we know that the dark matter or something like it is necessary even to explain structure formation in the universe. And it may be possible, there's strong indication that it's made of weakly interacting massive particles, which are their own antiparticles. So when they get together in regions of high density, they annihilate to form gamma rays. Those gamma rays have an energy given by E equals mc squared. So just about exactly, the energy would be exactly the rest mass if they just directly annihilated. So we might see a line in gamma rays at the rest mass of these dark matter particles. And that's expected to be somewhere right around the energy range where our detectors work, which is in the range of, like, say, 30 billion electron volts to 1 trillion electron volts. It's exactly where people, for various theoretical reasons, think you should look. So we may actually someday see such a line, or also see just a continuum spectrum from annihilation of these guys into other things like quarks and stuff like that. So my student and I actually looked at the most promising place, which was the galactic center. My student Carl Kosak at WashU a number of years ago. We actually discovered TeV gamma rays from the galactic center, but they had the wrong spectrum, and they're most probably associated with about 1 million solar mass black hole that we know to exist at the center of our own galaxy. But we're now building future experiments that will should have the sensitivity not just to see the galactic center, but to see a lot of other clumps of dark matter in nearby dwarf galaxies and so on. And we could really see a smoking gun signature of this spectrum from this dark matter annihilation, which would just be an amazing discovery. But who knows? I mean, maybe it's not even a particle, in which case we won't see it. Let's see, I am losing track of, let's see, I guess maybe this gentleman in the back in the white shirt probably is next.
The intentions of the
Yeah, it's kind of sad. It happened so long ago as to almost seem irrelevant.
So, you know, the distance between you're looking at and so forth now, and you get a hand, all this is very interesting, but what's the implication for people in understanding it? I mean, do we figure out that something's went wrong and we leave and go somewhere else?
Well, in terms of, okay, these supernova explosions would be a bad thing to be around, okay? It's kind of, they happen at a much higher rate in the center of our galaxy and in other galaxies, like a starburst galaxy, which is another one of our Veritas discoveries, something that has 10 times the supernova rate of our own galaxy. So it's kind of convenient that we're 24,000 light years from the galactic center, because chances are we might not have gotten the few billion years we needed to evolve life on this planet if we were closer to the center of the galaxy. That's another thing. Read this Rare Earth book. It's a great book. It talks about that kind of thing. So that would, you know, it would be bad to be near a supernova. So I guess the question is, another question might be, can we see something coming in time to get out of the way? I think that of all the things that look like a nearby supernova about to go, there's a star called Eta Carinae that looks like it's just about to blow up. It's blowing off wind. It's a supermassive star. It's pretty nearby, but I don't think it would really wipe out life on the Earth. It may make the atmosphere swell up a little bit and do some funny things. But it should be every 30 or 100 years we should see a supernova explosion in our galaxy. The problem is a lot of them are obscured. So the last one that was seen was about I guess 300 years ago. I'm not sure that it was seen. There's some debate, but it's certainly 900 years ago. The Crab Nebula was seen. I think, yeah, Tycho, I think. And when they are seen, they're bright enough that you can read a book at night, you know, if one goes off in our own galaxy. So they're not trivial events. So these kind of extreme events do happen in our galaxy from time to time. But there's one other interesting thing. Our sun is moving at a very large velocity. It apparently was thrown out of its stellar birthplace, which is also a good thing, because stellar birthplaces also tend to be stellar death places. Large stars live shorter time, live fast, die young. They blow up right away. So if you hang around in your birthplace, chances are you could be in trouble too. So we're kind of lucky that we're on our nice little sun was thrown away from its birthplace. So there's some relevance to life in all of this, I think. Let's see. I think this gentleman here in the...
You mentioned earlier that in a black hole that the conversion of matter to energy is about 30%.
Right. Or in accretion onto a black hole, it's about 30%.
I've heard as high as 50%. But
could be.
That's the most efficient engine, I guess, in the universe. Is there any energetic process that you know of, or that we have any that would be higher than that?
Annihilation, I guess. Annihilation converts all of the rest energy. So like, for example, these dark matter particles getting together, annihilating would convert all of their mass. The thing is, though, for dark matter to work, they have to be weakly interacting. So that means that they, like neutrinos that just book right through the Earth and are going through you at some ungodly rate all the time, these things have a similar kind of strength of interaction. So but yeah, something like a particle that's its own antiparticle getting together with itself and annihilating, that would be 100% efficient. So yeah, you're never going to do anything practical with it, but let's see. I think maybe this lady here.
You mentioned designing a new experiment with the Galactic Center. What does that mean? Is that new telescopes or new ways of looking at data, or what?
Yeah, it's actually another thing. Oh, those, by the way, are stars moving around the galactic center. So this is the thing I very much would like to build, which is an array of a new type of telescope, which is a very wide field of view, very high angular resolution. These things are big. These are the telescopes we build. They're like 40 feet across, the dishes. They're reflectors. They have very fast cameras that make like little movies where they take exposures every nanosecond. They're kind of crazy things. And we have an array of 4 of these now. The next step would be to build something like an array of 36 of these things of a better design. And there's a project called AGIS, that we're proposing right now, and it is currently being reviewed as part of the National Academy's or National Research Council's decadal review process, where they're prioritizing large experiments in astrophysics for the next 10 years. That's how our previous experiment, Veritas, was funded. It was ranked in the middle of the pack by this National Academy committee, and then it got built. So we're fighting for the next bigger thing. The last experiment cost $20 million of your dollars, your taxpayer dollars. The next one would probably cost 10 times that much, $200 million. The smallest satellite experiment you can build anymore is $600 million, just to set a scale. So, but yeah, this is specifically motivated. I would say half of the science is motivated by dark matter. Like the U.S. Department of Energy really is prioritizing that part of the science. Let's see. Is there this gentleman in the front has had his hand up for some time.
The astronaut falling into the black hole obviously has
Problems.
strength of material issues at a massive scale.
Yeah.
What about at a molecular or atomic scale? What happens to materials there?
Well, we could estimate it from my little formula, right? It's proportional to the force is proportional to the size. And, you know, the atomic forces that hold things together are very strong, so that's what you're competing with. So if you get to a scale of an angstrom, which is, or 10 angstroms or something like that, say 10 to the minus 9 meters, then that force would be 10 to the minus 9 times smaller. So you'd have just maybe 1,000 pounds of force or something, which probably isn't that much. So probably not much is happening on that scale. It's kind of interesting, though, isn't it, that, yeah, maybe things, it's kind of a good question, because are things like gas and molecular gas and stuff being changed near a black hole? Or, you know, I mean, that's the kind of question you might wonder about. So, but remember, it's not hopeless. A supermassive black hole, which we know to exist, would be just fine. You could survive. If that jet of that cauldron, you know, that's spewing out this relativistic jet didn't somehow kind of knock you down into your constituent particles first, you know, you'd be fine. Are there other questions, or? Well, not sure.